Today we're going to discuss word problems again. This time we're going to discuss inequality word problems. And I think the important pieces here again are going to be to define the variable. After we define what x is going to be, in this instance we'll write an inequality without the variable. And then we'll write an inequality with the variable. We'll solve for the variable. And then we'll interpret. So we'll write out a brief statement. Maybe this is a complete sentence, maybe it's not, but we're going to interpret our solution. We're going back to this canning company. This canning company packages tomato juice in 2-liter cylindrical cans. Find the radius of the cans if the cans have a surface area of less than 1,000 square meters. An important note here is the surface area no longer is exactly 1,000 square meters. Now the surface area is going to be less than 1,000 square meters. I actually made a small mistake in the last video about word problems. I put here that this was 1,000 cubic centimeters. If we're talking about area, we need to be square centimeters there, so I apologize for that typo. First thing we need to do, we need to define what x is going to be. X comes back to the question, we need to find the radius of the cans. This is going to be the radius of the cans, and I would imagine because our surface area is in square meters that this radius will be in centimeters. In this case we have two equations that are not going to involve the variable. Volume equals pi r squared h, and the second one is not actually an equation. Surface area needs to be less than 1,000. We can plug in for surface area. Surface area was the two bases, so 2 pi r squared plus the circumference times the height. That needs to be less than 1,000. We can start to substitute in now. Volume is 2 liters, which we know to be 2,000 cubic centimeters, equals pi, r we're going to call x, h we're going to leave in there. We isolated h there to be 2,000 divided by pi x squared. On the surface area equation we're going to plug in x everywhere we see r, and that needs to be less than 1,000. We're going to substitute in this quantity everywhere we see h. So I now have a new inequality of 2 pi x squared plus 2 pi x times 2,000 over pi x squared, which needs to be less than 1,000. I would simplify that just briefly to be 2 pi x squared plus the pi's are going to cancel, the x, a single x will cancel, I'll get 4,000 over x is less than 1,000. I'm going to struggle to solve this algebraically, but what I can do is I can go to my graphing calculator and I can compare the left side to the right side. And most importantly here, we need to recognize that we want this 1,000 to be bigger than the surface area. So here's my graph, y equals 1,000, and then the surface area equals 2 pi x squared plus 4,000x. It's important to note what the window looks like here. I'm going from an x value of 0 out to an x value of about 20. I'm going from a y value of 0 up to a y value of about 1,200 so that I can see these intersections. These intersections are going to occur at 4.619 and 9.655. We can find those in our TI calculator as well. Again, we're interested in the 1,000 being greater than. So if I'm finding these two intersections, I'm really interested in saying that my interval will be from 4.619 all the way out to 9.655. So coming back now to my problem, when is the left side less than 1,000? Well, that's going to occur from 4.619 all the way up until 9.655, and I solve for that graphically. To interpret my solution, this would be an interval of radius values, and the units on that are centimeters, where the volume equals 2 liters and the surface area is going to be less than 1,000 centimeters squared. We're going to look at a second problem here. A packaging company wishes to design boxes with a volume not more than 1,000 cubic centimeters. Squares are to be cut from the corners of a 12 by 15 inch flat sheet of cardboard, with the flaps folded up to make an open box. What size squares should be cut from the cardboard? It's important to recognize what's going on here. We have a flat sheet of cardboard. That flat sheet of cardboard is 15 inches by 12 inches. I'm going to cut a square from each corner. And when I cut a square from each of those corners, I can then fold along these blue dotted lines. And if I fold on these blue dotted lines after removing these corner squares, those are now gone, I will get the image above where I have a box with an open top. So, what do we need to do? We need to define our unknown. X equals the dimension of the square cut. And we're going to do this in inches. So I'm going to call X, 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 X. All these cut-ins are X. I'm now going to write an equation or an inequality without X. The volume, which is going to be length times width times height, needs to be not more than, so less than or equal to 1,000 cubic centimeters. So let's plug into this length, width, and height. Let's come back to our box image. The height of this box is going to be X. When we fold up those flaps, the box will come X units out of the screen. The other dimension we need to worry about is right here. This would be either the length or the width, and that's going to be normally 12, but I'm going to cut in X on each side, so this dimension is going to be 12 minus 2X. And then the same thing for the other dimension of the base. Normally 15, but I'm going to cut in X on each direction. This would be 15 minus 2X. So 15 minus 2X and 12 minus 2X times the height of X needs to be less than 100. If we were to graph these two sides, we should be able to get an image that will tell us when our box has a volume of less than 100. On the right side of this inequality, we have a cubic. This cubic is going to cross the x-axis at 0, this cubic is going to cross the x-axis at 6, and this cubic is going to cross the x-axis at 7.5, and it's going to have a normal end behavior for a cubic, so it's going to look something roughly like that. If I were to graph y equals 100, I would get this line right here that's going to intersect. It's important to recognize what window I'm interested in here. I'm really only interested in positive y values, which is a positive volume, and then I'm really only interested in x values up to 6. It would be impossible to cut in more than a 6. Because of the 12, I couldn't cut in 6 on the left and 6 on the right and still have a box. 6 is going to be my maximum. So now I'm going to go look at the graph. Here I see the volume, which equals X times the quantity 15 minus 2X times the quantity 12 minus 2X. That's showing up in red. And then I'm going to see the 100. My window here goes from 0 up to about 6 in the X direction, and it goes from 0 up to about 250 or 300 in the Y direction. I'm interested in these intersections. These intersections occur at 0.692 and also at 4.197, so it's important to note those. Coming back to my problem, what am I interested in? I'm interested in the volume being below or equal to the 100. When does that occur? The volume curve is going to be below the 100 from 0 all the way up to 0.692. It's going to be equivalent to the 100 at 0.692, so I'm going to include that. And then again, we're going to be below from 4.197 all the way up to 6. You can decide whether you want to include 6 or 0. I'm going to leave you with this question. Why am I not going beyond 6? Why did I stop at 6?